So, good morning to everyone. It's time to start again. And today we have a keynote speaker held by Professor Elena Pettinelli from the University of Roma Tre that has done, I don't want to destroy the surprise, among many other things, also a particular research that I read not from a journal, but from a newspaper. I identified her among also several other authors. I proposed to Sebastiano to invite Elena in particular because of several reasons, among which the surprise. Sebastiano said before then immediately. Elena, good morning. I can see you in the monitor. And
good morning
the floor
to
is for you.
Can you hear me? Everybody can hear me well?
Not yet. I see you because there is another monitor, but now I'm sure that you will be visible in a while in the monitor for the people. Yes, now,
okay.
now
Okay.
You are visible.
Okay, can you hear me? That's okay.
Yes, yes, yes.
Okay, I need to know now. I will put my slide on and see if we can if you can see me. Okay. I need to know if you see my presentation. Is that okay? Raffaele, can you give me
yes,
some
yes, Elena. Yeah, yes, Elena. We see
okay.
your presentation.
Okay, thank you very much. Okay, good morning to everybody. I'm sorry to not be there, but you can understand well the situation, how it's evolving for the world. It's the first time I do something for IWAGPR that I'm presenting something that I'm not there. It's very peculiar. So the keynotes that I'm presenting today regards the use of GPR. So we are all interested in this, but it's the use of GPR in a special condition. So I'm gonna introduce the use of GPR for planetary exploration, and in particular for the search for liquid water under the polar cap on Mars. Because of course this is an issue that not many people know in terms of GPR development for planetary exploration, and in terms of the problem of looking for liquid water on Mars. I will introduce the problem of exploring other planets with geophysics first, and then we will enter specifically on the issue of looking for water with GPR. Okay, so I'll give you a little bit of background about what is going on, what was the past of the exploration of other planets, in particular Mars, as you can see here. So as you can see from this slide, Mars has been visited many times. So we are talking about the beginning of the 70s or so. There have been many attempts and some successful missions to Mars. First, using flybys and orbiting spacecraft, and then using some landing, some landers, and eventually some rovers. And now, as you can see from this slide, MARSIS has been explored extensively. We had several very successful missions, and as you can see here, there is also some future proposals. So where we are now, probably you all know that this year, 3 missions successful arrived to Mars. The last 3 missions were one from the Emirates, one from the Chinese Space Agency, and one from the United States, from NASA, which is called 2020 Mars. The Chinese, just to give you an idea, sent to Mars successfully landed a lander, a rover, and an orbiter. And the rover is equipped with 2 GPRs. I'm not going to talk about this today, with 2, one high and one low frequency GPR. And there is also a GPR, sort of GPRs on the orbiter. So as you can see, there is a large interest in exploring with geophysics the planet. And the main reason for this, as you can see from the slide, is looking for water. So we're gonna start talking about this first, and then we see how much water is left on Mars. First of all, we should say why we are looking for water. Well, this is, let's say, it's a simple question in some way, but because water is linked to life, at least the way we know life has been developed on Earth. So we look for water on other planets, and you might be surprised to see how much water there is on any planet of the solar system, in different forms, of course. But Mars is special in many respects. So the idea to go to search for water on Mars is pushed by the need to understanding if life was something very peculiar of our planet, or if life tried to develop on other planets, and from some reasons never developed the way that happened on Earth. So Mars is a special place, and I will show you in a moment why. As you can see here, we know that life can develop in very extreme conditions. We know on Earth that life can develop at the bottom of the sea, for example, in sea vents. We know bacteria there, or in very hot springs like Yellowstone, or in Antarctica subglacial lakes, which is probably the most is the proxy in some way, the closest environment, as we will see for Mars, something very similar in some way. That's what we think. Life also developed in very dry conditions like the Atacama Desert. So we are asking why life could have, if life could have been developed in the subsurface of Mars as well. So a little background on Earth versus Mars. Mars, as you can see, is much smaller than the Earth. Here there are some general information about Mars, like the radius, the gravity, the length of the day, as you can see, is very similar to our day. The length of the year is double, and the inclination of the axis, for example, is similar. But if you look at average density of the rock, of the solid planet, is, for example, lower. Okay. The most important thing to look at is the average temperature on the surface, because this has a large impact on water, on possibility to have water in some form on the surface. So on Earth, the temperature is the average is 14 degrees, and you can see how cold is now Mars. The average temperature is -55. Okay. Why we think that Mars still has or maybe had, we're sure we had the water in the past. This comes from what we know from the earlier missions to Mars. These are all but important pictures in the history of what we know about Mars. These are pictures taken by Mariner 9. And from Mariner 9, what we've seen that the Mars had some geomorphology, some structure on the surface that really remember recall us the presence of rivers or lakes or structures linked to a certain amount of water. This is, for example, is a channel. This channel is 600-meter long and is draining, seems to, in the past, drain in an important crater, which is a Gusev crater. So starting from this pioneering imaging or images of the first missions, of course, our ideas progressively develop on the history of Mars. What I can show you here is what we think happened to Mars in the course of his geological history. Hope this can be seen. This is starting from 4 billion years ago. We think that especially in the northern part of Mars, there was a large ocean, and progressively this water disappeared in time. So we are talking about water just in the first half billion years of the history of Mars. So as you can see, progressively this water, at least this water on the surface, mainly disappeared. So what if you look at the graph of the stability of water, Earth is this yellow bar, and Mars is now on this red bar. But we think that in the past, Mars was more similar to the condition of the Earth right at present. So why this water disappeared? I can show you here a picture that summarizes what probably happened. Mars is small, doesn't have a magnetic field, so it doesn't have protection like us from Van Allen belt or the magnetic field of the Earth. So progressively, Mars lost his atmosphere. So the small atmosphere that was there before was progressively eroded by the solar wind. And of course, once the atmosphere was getting thinner and thinner, of course, the majority of the water was basically sucked out in space. This loss of water was investigated for a long time, because the main question was, but Mars lost all his water, or some water remained in some form on the surface. I can't show you what we know now, because Mars has been progressively, as I said, investigated by more sophisticated instruments and missions in time. And so we know that now there is a fair amount of water in the form of water ice on Mars in different areas. The map you see on the right is a map of gamma ray spectrometer, which measured the quantity of water ice in the first meter in the subsurface, probably ice trapped in the pores of the sediments of the regolith or the sediments in the first meter. So you can see there is a fair amount of ice, but this is an image made by a GPR called Charade, which is a 20 megahertz orbiting radar that shows the existence of some layers of soil and some and a certain amount of ice inside this soil in the first few meters. So although Mars lost a large quantity of water, we still think and we know now that in several parts some of the ice has been preserved. So of course the majority of the water ice is sequestered in the polar caps. As you can see, this is the left is a north cap of Mars, and the right is the south polar cap. And here there is this is the main reservoir of water ice of the planet. But we are still thinking that there might be some water still trapped in the subsurface. Here, just to show you that there is a sort of seasonal cycle of the water caps of Mars that are changing during the Martian year. Just to add one more information, especially the south polar caps is mainly made by water ice, but there is a fair amount of dry ice, so CO2 ice intermixed at the top, especially at the top part of the polar caps, which is called the residual polar cap. Okay, now we go towards the idea of looking for water, liquid waters in the subsurface. So for many years it has been hypothesized that some of the water was also trapped in the subsurface, and some of this water at a certain depth could have been could stay in the liquid states given the temperature in the subsurface. So the idea basically is schematically described in this sketch, where the hypothesis, the main hypothesis, were that there was some ice below the soil, so it trapped in the pores, and below that some groundwater. So the question was how I can detect the water at such depth below the Martian the regolith of the rocks of the first layer of rock. And of course, what was thought is the idea to look for to use some geophysical equipment to try to investigate the subsurface. Of course, things are very complicated because I have to make a mission with some instrument and put some instrument on an orbiter system first. Okay, so where we took the idea was taken by a condition that a type of application of geophysics that all the GPR experts know quite well. The fact to use some radio waves to investigate below the ice in Antarctica, and I would say not only in Antarctica, but in Greenland and in other areas where the ice is thick. So the idea came from what we know well, the development of some radar capable to fly high on an orbiter and investigate the ice to look for water below the ice, especially below the polar caps. Exactly what the same we do when we investigate the lake in Antarctica. You probably know that the majority of the lakes in Antarctica has been detected by GPR, called in that case radar echo sounder, but it's the same concept. And actually, I think more than 400 lakes has been detected, and the majority of these lakes has been detected with ground penetrating radar or radio echo sounder. Okay, so there is another important aspect in exploring the planets that help the idea of using radio waves, because the planets have essentially two conditions: a very dry condition, like the surface of the moon, for example, or the surface of Mars, and very cold. As you know, in this condition, so a dry and cold environment is a perfect environment for radio waves to propagate in a material. So the attenuation is much reduced. And it's much different from what we are used to have on Earth. So in this condition, of course, using a radio wave is probably the best idea in terms of what kind of geophysical tool can be used on a flying on a spacecraft, on an orbiter. In particular, if you look at the behavior of some materials in terms of response attenuation as a function of temperature, we can see here, especially if you look at the temperature condition of some planets, like Mars, not only Mars, for example, the Moon in some conditions, but some planets, as you can see, the blue line is, for example, water ice, like typical of the polar caps of Mars. And as you can see, this graph has been calculated for 4 megahertz, for a frequency of 4 megahertz. As you can see, the attenuation is plummeting from high temperature to low temperature. If you mix the water ice with some sediments, what is called here dirty ice, you already see that the behavior is a little bit different. Okay, if we look for rock, the response, the attenuation is essentially temperature independent. So we have different behavior of different materials. Okay, so water ice is particularly suitable for radar sounder investigation due to this particular behavior in terms of temperature. Okay, and as you can see here, this is an image of the layer deposit on the South Pole. So the South Pole is made with ice, but is also made with the layers probably intercalated with layer of dust. So we come to the idea in the late 1990s. The Italian Space Agency had the idea to propose to NASA and to ESA for the next Mars Express, which is an ESA spacecraft, so European spacecraft, to put on board a sort of GPR, very low frequency GPR, to investigate, to search for water at large depth. We are talking about looking for water at several kilometer depth in the Martian subsurface. And the idea of the Italian Space Agency was that of ask to Giovanni Picardi, as you can see here, which was a professor in radar investigation at La Sapienza, to design the radar. And the radar was built during the late 1990s and the beginning of the 2000s with a collaboration between ESA and the JPL at NASA. And the radar that you can see here in the picture, because you cannot really see the radar because of course the antenna was open later. The radar has an antenna of 40-meter length, so something really, really big. And the Mars Express was finally launched in June 2003 and arrived in December for Christmas 2003 in the orbit, orbiting around Mars. The antenna of MARSIS have been opened much later, so around the summer of 2005. The reason for this is that this antenna was folded. You see here a sketch, but the antenna was completely folded, like a wooden meter was folded inside two boxes. And of course, on Earth, nothing could have been tested. Something like this was projected, was designed, sent to Mars, and actually open without any test on the Earth because the system was too big. So they were worried that at the beginning that the opening of this large antenna was going to destabilize the spacecraft. So they wait for a long time, and finally they open the radar. So you can see here some information. The radar works at different frequencies, 1.8, 3, 4, and 5 megahertz. The problem is that Mars has a large ionospheric effect, so the frequency has to be below this effect to minimize the noise produced by the ionosphere, and has to, of course, have the characteristic to reach few kilometers in the subsurface of Mars. So this was the final choice of the frequencies of this radar, and is a chirp signal set by the system. Here you can see some information about the center frequency, the bandwidth, and the power. So this system, of course, work in a way that you can imagine. So is a radar sounder, and the idea is to investigate the entire planet. So progressively making orbits and acquiring data, not only on the poles, but also in other parts of the planets. At the end, it results that the only place where Mars really see well below the surface is actually the North and the South Pole. There are other areas where data reported some stratigraphy in the subsurface, but mainly the radar was working on the poles. So of course the scientific community concentrate on the information coming from the poles. Okay, so if you go back to the materials I was showing before, we can see one moment a real imaginary part of these materials. The gray bar give you information about the frequency range of MARSIS. We said this range is from 1.8 to 5 megahertz. Just to give you more information, when the radar acquires, it can acquire just in 2 frequencies. So if you select the 1.8, you can have 1.8 and 3, or 3 and 4, or 4 and 5. Okay, 1.8 was basically the frequency that was used the last because it was very noisy. So probably the best frequency of all is 4 megahertz, 4 and 5 megahertz. So here you can see what is expected in terms of propagation of MARSIS radar, MARSIS signal in the polar caps, and the general behavior that we expected in presence of rock. If below the ice at the South Pole or North Pole there was rock, if there was saturated sediments, or if there was actually water. Okay, so the idea was to investigate well the poles area to see if there was some sign of water in the subsurface. So in reality, what MARSIS recorded this kind of signal in a very schematic and simple way. So in this way, we could see where was the surface, considering that the spacecraft is flying at the altitude from the surface of Mars, which is between 400 and 800 kilometers. So you can also imagine how big is the footprint of this radar. We're talking about a footprint of about 5 kilometers. Okay, 5 kilometers to 7 kilometers. So it's a huge footprint. Of course, what you can see in the subsurface in the signals is when the signal propagate at the bottom of the ice, we see some of the signals. In a minute, I will show you real data. Okay, so we are able to detect the surface and detect the base of the ice deposit at the polar caps. Okay, so and we also have some additional information. We know that mainly this layer, this structure is water ice, so we can guess in some way what could be the permittivity of this material. Of course, it's not pure ice. In the North Pole, the ice is pure. The South Pole is much more mixed with sand. We can see from optical images the layering, as I showed you before. So we can make some assumption of the properties of this material, which is really important to try to guess what is under. Okay, so what can be done from a quantitative point of view using GPR to have some information from the reflection of this signal at the base of the polar cap, to have some quantitative information about the material below. I can show you real data, so you have a much better picture of what MARSIS collect. Here you see a radargram. You are all used to see radargram, although the radargram of Mars are quite peculiar in some way. And this is a movie that we built. You can see here two things. The red dot is the reflection from the surface, remembering that we are flying very high with this system. And the blue dot is the reflection from the subsurface. You can see also from this radargram there are some layers inside, but we don't concentrate now on this. We concentrate only on the surface and the basal reflection. And what you see here is what we could call the radar profile. Okay, so it's a segment of the orbit where the radar was acquiring the data. This is the South Pole, and this is the area where we concentrated on doing our analysis. Why we concentrated on this area? Because this area was studied very well by Picardi, also from using other information. And this area has a very, very flat surface. Of course, you can imagine that because we are flying on top, any geomorphology or any morphological structure or changes will create images in the subsurface that are due to the topography and not to the effectively what is in the subsurface. So the idea is to look for very flat area, extremely flat area with respect to the wavelength of the radar, to minimize the effect of the surface, and so try to investigate the subsurface. As you can see in this, I'm running this. If you can see once in a while that the subsurface reflection is even higher than the surface. This is very specific things. We don't see in GPR that we use on Earth. The GPR is on the soil, and this is always larger than the reflection at the base. In this case, it's not, because depends on the material on top. Okay, so this is what we notice in this area. When we start analyzing with Picardi this specific area, which is called Ultimi Scopoli in the South Pole, we start seeing this effect. The fact that sometimes in some area, the reflection from the subsurface was much higher than the surrounding, but also higher than the surface. So this happened way back in time, because this observation was made around 2008. This is a very old plot of the first few years of investigation of that area. And in the first year was happening something very, very strange, because MARSIS was passing on the South Pole several times in the years and in several directions. We were noticing something that was extremely strange, that some area where we could see high reflection, which are these blue dots, large blots, sometimes the same area investigated in the other direction was giving a reflection at the base very low. So this inconsistent behavior took us a long time to be clarified. The reason of this behavior was discovered several years later. So it took us a good 3 or 4 years to understand why there was this very strange behavior. And I show you this picture. This behavior was due to onboard processing. As you can imagine, some of the data collected was onboard processed to reduce the amount of data that should have transmitted to Earth. So at the beginning, when the radar was designed, it was decided to put some processing and put some pre-summing of several traces collected one close to the other. This pre-summing was poorly made, let's say. And so the top picture, as you can see, was the results of onboard processing. We decided to ask to ESA if we could acquire some data without the processing on board. This was discussed at length, because usually when you have a mission ongoing, you don't change from Earth the parameters, because you risk to also create other problems. We convinced the ESA to change this, and this is the similar section of this. Actually, it's the same section collected without onboard processing. And this data is much clearer. When we start acquiring data in the same area, so Ultimi Scopoli, without the onboard processing, many questions, for example, this inconsistency was solved. I can show you a reconstruction of the area of data collected without onboard processing. These are orbits, and this indicated the footprint. These are different orbits collected in different moments. And as you can see, look at the blue line, blue area, sorry, I can show you back. The data start to be consistent. So when we see high reflection from the base, in one orbit, we see a reflection from the base also in the other orbits. And this is basically the end of 2005 in this history. So once we had that data, we start thinking about inversion. And how this inversion was made, we suppose our structure made of 3 layers. The atmosphere, where the permittivity is 1, the pole, the ice, where the permittivity was considered the permittivity of water ice, and the third layer, which is the permittivity we want to calculate. Okay, so starting from this model, we had to assume known the properties of this material, but this can be done because we have a certain knowledge of the characteristic of the polar cap. And so we're trying to invert the data as, with a probabilistic approach to estimate the basal permittivity. I go in a little bit of detail because this is important to understand what we were doing. So MARSIS can retrieve the permittivity. So we could retrieve the permittivity of the basal material from the amplitude of the reflected signal, which is, of course, known to everybody. So the reflection, the amplitude is in general a complex quantity, okay? Where epsilon 1 is the complex permittivity of the first layer, and epsilon 2 is the complex permittivity of the basal material we are interested to, okay? And this complex material, of course, accounted for in the imaginary part of both the effect of loss due to polarization, loss due to conduction. Okay, however, we don't have the information on singular polarity, so we have just information. So the only parameter we can estimate is the modulus of gamma 1, 2, okay, which is, of course, a real quantity. So from this modulus, we can try to estimate this value, which we call epsilon apparent permittivity, epsilon apparent, okay, the apparent permittivity of the basal layer. Under some assumption, we can assume, for example, that because the polar ice is made by ice, we can, with a little bit of unmixed dust, we can assume that the epsilon double prime is negligible, okay? So no loss. Under this assumption, we can estimate the permittivity of the second layer, which we call the apparent permittivity, which is expressed by this equation, okay? The apparent permittivity is a real quantity, okay? But is a real quantity, as you can see here, there is in the modulus the permittivity of the complex permittivity is the modulus of the complex permittivity, the second layer, is a real quantity that accounts for both polarization and conductive process. So it's a full information, but represented by one quantity, okay? There has been some confusion in understanding what is this parameter, this real quantity. This is not the real part of permittivity of the second material, but it's a real quantity, okay? So to make it short, this story, what we did, we inverted the data, assuming certain characteristic of the first material, and we found two populations. We found that we express the probability function, okay, is the probability function of a normalized basal echo power. Normalized to PS is the power of the surface signal, the signal reflected by the surface, and PSS, the one reflected by the subsurface. So we find two populations, and from these two populations, we inverted the data, and we found two populations of permittivity of the subsurface. These two populations have a median value that are very different. The median value of 4 megahertz for the population of the reflection from the rock is about 7, and the median of the distribution is about 33. So from this data, this is a paper published in 2018 on Science. We could infer that in some area where the reflectivity of the basal material is very high, probably there was some liquid water or sediment with some water, so partially saturated sediment of some sort, or ponded water of some form. So this was the final result of this paper published. Okay, so the final result was basically the idea that there is an area here, these bright reflectors, this bright reflector area that is probably due to the presence of liquid water. So what happened after? Of course, there are some problems, some clear problems with this interpretation. The main problem, which was raised by Sorin and Bramson paper a year after, is the flux, the thermal flux at the base of the ice. From modeling, there's no measurement on heat flux on Mars yet. The only probe that I was sent to do this wasn't working, so we could not have any information. From modeling and from rigidity of the lithosphere, it has been suggested that the flux, the heat flux at the base of the ice is too low to support water. So basically, some of the calculations suggest that the temperature at the base of the ice is of the order of 180 K, so a value very low. In the paper, in the science paper, we suggested that the water was salty. So, and this is also supported by the fact that on Mars, some special salt that depress very much the temperature at which the water is solid. We're talking about the pressing of 70 degrees, about 70 degrees. These salts are perchlorates, are ubiquitous on Mars. They could be mixed in the water at the base of the polar cap. Okay. Few information came out. In the meantime, we were doing publishing the article. For example, they found using radar echo sounder, they find the first salty lakes in the Canadian Arctic, which did not supposed to be there. So it's something, it's like a condition similar to what we find on Mars. These lakes are at a temperature of about -20, and this water should not be here. But they found that these two lakes are salty. So a condition that we can consider similar to what we found on Mars. So after that, more data were acquired. We keep on acquiring data on this area because we were interested in investigate more. And so the original paper was based only on 29 observations. Here we had 134 observations, so we investigate at length this area. And we had another idea. Because our paper was raising a series of questions, we had an idea to trying to use an independent way to prove that there was water at the base. And what we did, we used the criteria that is used in Antarctica to define if is a bright reflection is due to water or some other conditions. Okay. And as you can see, this is actually data from Greenland. As you can see, they have in Greenland, they have distribution that are very similar to the distribution we found for our probability density values on Mars. So we were interested in testing this hypothesis. So we're trying to apply to the data all the criteria possible for MARSIS that was also used in Antarctica and Greenland. So we use several criteria to define if the reflectivity we were saying could be attributed to water or not. And we use three criteria, which are the echo strength relative to immediate surrounding, the specularity, so how flat, how specular is the reflection, or the absolute echo strength. So we applied this criteria in a new paper. This paper was published at the beginning of this year, actually at the end of 2020 on Nature Astronomy. And these are the results. As you can see, the area, we enlarged the area. So we see not only the main area that was seen in the other paper, but other areas where we had high reflectivity, high specularity, okay, and other criteria satisfied. So we took this data and we made a map of the permittivity of the area. After that, this is the last issue, maybe we can discuss if you have questions. After that, there were published 3 papers saying that maybe this is not water, maybe this can be clay, for example, clay material or saline ice. So the paper from Schroeder and Stromberg was a commentary to these 3 other papers that were challenging our interpretation, suggesting different hypotheses. I can quickly say that these 2 hypotheses cannot be supported by laboratory and electromagnetic theory, because, for example, it's well known that clays at low frequency have a very low permittivity. There is a large amount of literature data on this. So clay cannot be high reflective materials at 180 K or even at 200 K in temperature. And this is the same for saline ice, unless there are brines inside, so liquid water, and we go back to our original suggestion. If there's no liquid water inside the salt, the salty ice, this cannot be reflective at such a low temperature. So this brings back to idea that here there might be liquid brines. Of course, there is a problem, is reconcile this interpretation with the temperature at the base. So we are now at the point that we are trying to investigate in laboratory, and we are doing this work in 2 laboratories, one in Italy and one in the States, to understand if there are some sort of brines that can remain liquid for a long time at such a low temperature. And there are some interesting results. I would say that these results will be presented at AGU in 2 weeks from now. This is the point where we are at, and I thank you for the attention. And if you have any question or comment, please. I leave you back the word to the conference.
Thank you, Elena. Thank you very much. I don't see the portable microphone, so please, if there is any question, I would pray people to come here and to speak in one of those microphones. Is there any question? Elena, please, just by myself. First of all, a curiosity. I've never worked on those topics, but I remember some years ago, there was the hypothesis that the Martian soil might have magnetic properties, but I didn't see throughout your presentation. Is this hypothesis abandoned?
Yes, when they think about using the radar, one of the questions was, there is a microphone return. I can hear myself. Okay, thanks, Raffaele. Yes, at the beginning, there was some hypothesis. Mars is a red planet, and there was the idea that the majority of the soil of the regolith was magnetic. There has been done several measurements, not only from by our laboratory, by other laboratories around the world, studying the electromagnetic properties of hematite, of magnetite, or other materials. And that was a concern mainly for the propagation in the subsurface, but it came out that you should have so much magnetic materials to create a problem that this is not the case for the surface. Too much for Mars, and there is no such a high level of magnetic materials in the soil.
And just another question. I understood that the model is 1D model, no, from your formula. But forgive me for the elementarity of the question. I saw the formula retrieved on 2 materials, no, yeah. On a half space. If there is the lake under the soil, I would not expect at the first site formula based on 3 materials, no, on some transportation of the equivalent impedance accounting from the depth of the liquid lake.
Well, what we are thinking is actually now the problem of the lake, the term lake wasn't exactly what we used at the beginning. That was much more introduced by the press than us. So what we said is the material below the ice might be wet. So we're not talking about a lake. We're talking about some material, some soil probably, which is partially saturated, or there is a thin layer of water. So in that respect, we can accept that the simple modeling. On the other hand, it's very difficult to make a more advanced model, Raffaele, because the controlling this data, you see how the information comes, and the fact that you have an object that is basically every time it looks down, it looks at an area of 5 by 5 or a little less kilometers. It's difficult to think about a much more refined approach.
Okay, as you know, I read it from the Repubblica, La Repubblica newspapers, and so yeah. They say the lake.
Yeah,
there is
no,
another question.
What an interesting paper and research. I had a question that I don't understand. So if the polar caps are changing over time, I didn't understand the mechanism for that, but also does it change the data since you're collecting over many periods? Did it affect your measurement at all?
The polar have a seasonal change, if you refer. The polar have a seasonal change in terms of depositing and sublimation of CO2 ice. This is the type of seasonal change that Mars can have now. Mars has a very thin atmosphere. It's 1/100th of the atmosphere of the Earth, so it has a sort of season, but that doesn't affect the water ice. So yes, in some areas during different period of the year, you could see more or less a thicker or thinner or an absence of CO2 layer on top. And this can have some effect because the permittivity of the CO2 layer is about 2 if it's a solid ice, or if it's a snow of CO2 is 1.7, let's say, that has been measured in the lab. And so the reflectivity from the surface can change. This is the change that can be seen, and especially seen at a higher frequency. There is another orbiting radar called SHARAD I just mentioned that works at 20 megahertz. It looks much more a GPR than MARSIS, and can see some of this tiny change, but definitely it doesn't affect the measurement we are doing. When we pass in these years, we were seeing the same thing once we understood what was the problem.
So I have another question. Thanks for the presentation. It was really wonderful. Maybe I missed this part of information, but why don't you record the polarity of the wave?
because MARSIS can't, it doesn't send this information. We don't have it. We just have the amplitude of the signal. It's not submitted to the data. It was just a process for the amplitude. Okay, unfortunately. So it's nothing that can be done.
Any other question? So I don't see any other question. Thanks again to Elena. Thank you very much.
Thank you to you. Good work.
See you soon, Elena.
See you soon. Thanks.
Bye.